if you see in the previous video, it's really quite a simple schematic. We have our low dropout voltage regulator here connected to the battery with input and output caps as usual. We have our peak micro here, which is low side switching and LED. We also have our motion sensor powered by the low dropout regulator, as well as our peak, and it's connected to our peak via GP3. There are some good hardware options here. We can pop in a high side switch of some sort here just after the batteries that will turn off when the battery voltage drops below the desired cutoff threshold. Or we can do a low side switch here. There are many different solutions for that, but we want to keep things simple and explore if we can do a software-based solution without any changes to the hardware. Most microcontrollers like PIC10F with wide operating voltages have an internal fixed voltage reference for accurate analog readings. We can utilize this to measure VDD and shut everything down when it's below the desired cutoff point. In this case, our micro can only shut down the LED and itself, while the regulator and the motion sensor will still consume some standby current, but that should give us a few months to save the batteries before overdischarge happens. Also, since our micro is behind the regulator, our VDD readings will be slightly lower than the actual battery voltage, but it's a small, almost constant drop we already know, easy to incorporate into our threshold. Before jumping into the code, let's have a look at the datasheet for PIC10F. Under the analog to digital converter section, we have all the information needed. First, the voltage reference. The AD converter reference voltage will always be VDD. So what this means is that for our 8-bit AD converter, this means any analog signal at VDD will read as 255 and linearly go down from there till 0 volts. Next bit we need is the internal absolute reference. So the function of internal absolute voltage reference is to provide a constant voltage for conversion across the device's VDD supply range. An internal absolute voltage reference is pretty common in micros with wide operating ranges because you need some sort of fixed point to get accurate analog digital conversion results within the operating range of the microcontroller. So there is an equation here which is quite useful for our case. It states that conversion result equals to 0.6 volts divided by VDD divided by 256. And with this equation, we can measure where our VDD is. So let me pop this one into a spreadsheet. Now we have 3 bits of information that we need. We have our battery voltage, and we have our supply voltage going to the micro. This is behind our linear regulator, and we have the conversion result from our internal fixed voltage reference. I'm just going to pop the formula here, which is 0.6 divided by B4 divided by 256. Now let's put some sample battery voltages here. Let's say our battery voltage is 4.2 volts. For our 3-cell nickel metal hydride pack, fully charged at maximum health, then our voltage regulator will regulate it to 3.3 volts, and that would give us a conversion result of 46. So now let's copy this one all the way down. We can look at different voltages. So if our battery is at 3.6 volts, then our regulator have a dropout of 0.3 volts, and we'll put it at 3.3 volts again. So no change. But here's the funny thing that happens. If our battery voltage is at 3.3 volts, now at this point in time, our regulator will not be able to regulate it anymore because the regulator needs a 0.2, 0.3 volt voltage for regulation to happen. So we will get something quite close to 3.2 volts. That will give us 48. If you go lower than that, let's say our battery is at 3 volts, then our regulator will pretty much output 3 volts with like 0.1 volt dropout. It has some sort of internal resistance, but at this point, it's not regulating anymore. It's just doing its best to output anything that's as close as possible to the input. And then our conversion result would be 51. So if you go all the way down to 2.7 volts, which is where overdischarge will start to happen, and our VDD will be very close to 2.7 volts again. At this point, we will be reading 56. As you might have already noticed, as our supply voltage goes down, our conversion result linearly goes up. And that's because the proportion of 0.6 volts to our supply voltage is getting larger and larger. And that's why this is happening. So looking at these numbers, 3.2 volts seems like a good cutoff voltage, because at this level our motion sensor won't be operating properly, and from a state of charge point of view, our batteries are almost completely depleted. There's not much left in a nickel metal hydride battery below 1.1 volts, and it will give us some sort of slack if one of the batteries are discharged more than the others. So, and the conversion result for 3.2 volts is 48. So we can safely assume if the conversion result is greater than 48, our VDD is lower than 3.2, and that means our battery voltage is lower than 3.3. Now let's jump into the code.